Welcome back to our third discussion of AC power for power calculations in sinusoidal circuits. Today we're going to introduce another concept which is actually my favorite in AC power. It's the concept of complex power, and it's another definition we'll give you and how to calculate it. But complex power is my favorite because once you compute complex power, you really can answer all of the questions that ever crop up with AC power. So it just basically summarizes everything we've done so far. So let's dive in. Let's consider the quantity S, where S equals the complex product of V I conjugate. So here we have our same scenario where we have a circuit element that's got a current phasor, I RMS angle phi, and that current's directed into a voltage phasor, V RMS angle theta. So this, of course, is the I phasor, and this, of course, is the V phasor. So let's calculate the VI conjugate product. And so V, of course, is going to be V RMS angle theta. And the complex conjugate of I is going to have the same size, it's going to be I RMS, but the angle, instead of being phi, is going to be minus phi. So when you multiply those two together, of course you multiply the magnitudes and you add the angles, you get I RMS angle theta minus phi, and then we apply Euler's identity, and we see that S, which is VI conjugate, defined as VI conjugate, is V RMS I RMS cosine theta minus phi plus J V RMS I RMS sine theta minus phi. And if you look at this result, you say this is familiar because this is the real or the average power. And this term, the imaginary part, is the reactive power. So if we calculate this value, which is called the complex power, VI conjugate, V, of course, is a complex number because it is a phasor, it's the voltage phasor. I is a complex number because it is the current phasor. So VI conjugate is going to be a complex number. And when you calculate that complex number, the real part of the complex number, the real part of S, is the real or average power that we've been talking about, and the imaginary part of S is the reactive power. So if you just do this one complex number calculation, it actually gives you two of the numbers that we've been deriving in these talks. Well, let's look at S a little bit more. Let's actually take S and let's find the magnitude of S. So S, of course, is the complex power, and it's equal to VI, where V is the phasor, I is VI conjugate, where V and I are the phasors of a particular AC circuit element. Well, to do the magnitude of a complex number, the magnitude of a complex number is found by doing the square root of the complex number times its own complex conjugate. So the magnitude of S is the square root of S conjugate. Of course, S is going to be V RMS angles theta times I RMS angle minus phi. S conjugate is V RMS angle minus theta times I RMS angle phi. And then when you combine those together and collect all the terms, you see that the magnitude of S ends up being equal to V RMS I RMS, and that we've seen before. That is the apparent power. So if you do S equals VI conjugate, it's going to be a complex number. The real and imaginary part tell you the real power and the reactive power, and if you look at it from its polar representation, the magnitude of S tells you the apparent power. Matter of fact, there's even more than that. If we take the power triangle and update it with our new information, we see that S actually is this point out here if this is to be viewed as a complex plane. So if this is the real axis and going up in this direction is the imaginary axis, then S is this point in the complex plane, VI conjugate. And as we just saw, if you proceed this direction, that's the real part, and then you go up this way, that's the reactive power. Or you can go this direction, that distance is the apparent power, and the angle that you get, S equals VI conjugate, is going to be a real part plus an imaginary part, and that's the real power and the reactive power, or it's the apparent power, and the angle of this complex number is going to be theta minus phi, which is what we have written at the bottom. So the with the simple product VI conjugate, it's going to be a complex number. If you look at the complex power as a real and an imaginary number, in rectangular, it tells you the real power and the reactive power. If you take S and look at it in polar form, then the magnitude of that is the apparent power, and the angle is theta minus phi. So I love the complex power because it tells you everything you need to know about your powers simply by doing one complex product VI conjugate and then examining the result. So let's look at a summary here of all of our powers, and this is a chart you want to really spend some time and stare at and commit to memory, and it really helps you understand what's going on. So if we have an AC power, if we have a resistive load, then the impedance is simply a resistance. There is no reactance, and if you were to plot where this impedance lies in the complex plane, you'll see that that impedance is going to fall on the real axis because resistances are purely real. And so we see the impedance is on the real axis. Also, since the impedance of a resistor is really R angle 0, we know that theta and phi are going to be the same value because the impedance of the resistor is not going to change phi and theta and they're going to be the same value. So theta minus phi is going to be equal to 0. So if you were to take your current phasor and your voltage phasor when it's hitting a resistor, what you get is a diagram that looks sort of like this, where the current phasor and the voltage phasor lie along the same line. And in that case, if you were to look at these are sinusoids, and if you were to watch them on an oscilloscope, you would see that the current and the voltage would peak at the exact same time, and so we'd say the current is in phase with the voltage. Now, of course, remember that the power factor is written as the cosine of theta minus phi. Of course, theta and phi are the same thing. Cosine is 0. The power factor of a resistor is 1.0, and there is no reactive power in a resistor because theta and phi are the same. So now if we were to go over and look at an inductive load, of course it's going to have an impedance R plus jx. Now it's an inductive load. That the reactance in the impedance is going to be positive because it's j omega L. And then the impedance, if you were to plot it on a complex plane, is going to be out in the first quadrant because you have a real part which is going to send you out the real axis, and then the reactance is going to send you up, and so your impedance is going to live up in the first quadrant somewhere. Now if you were to plot your thetas and phis, because remember V equals I times Z, and since the angle of your inductance is positive because you're up here in the first quadrant, you're going to see that theta minus phi is going to be positive. Theta is going to be a bigger number, a larger number than phi, because it's going to be phi plus something, some angle up in the first quadrant. And so if you were to plot your voltage and current phasors in the complex plane, you would get a diagram that looks something like this. If you were to watch the voltages and currents go by on an oscilloscope, you would see the voltage peak first, then the current would peak later. And that is, the current is lagging the voltage if you were watching on an oscilloscope. Now remember once again that the power factor is the cosine of theta minus phi. And remember, cosine's an even function, and so whether theta minus phi is positive or theta minus phi is negative, you're going to get the same power factor. So some information is lost. So what we want to do is we want to retain that information. So since theta minus phi is positive, we are going to say the power factor is lagging. Of course, the cosine of theta minus phi is going to be less than 1 since we have an inductive load, but we want to keep the information theta minus phi is a positive number, so we say it's lagging, and that comes from the fact that the current lags the voltage if you were to watch it on an oscilloscope. So an inductive load has a lagging power factor. If you were to draw the complex power vector on the plane, you would see it lives up in the first quadrant as well, and because of that, the reactive power of an inductive load is positive. And finally, a capacitive load. A capacitive load, of course, has got written R plus JX, but in this case, the X, the reactance, is going to be a negative value, because remember, it's minus J over omega C. And so if you were to draw a picture of the impedance in the complex plane for a capacitive load, you'd go out the resistive direction, then the capacitance will send you down this direction. So your impedance, your Z impedance, is going to be in the fourth quadrant. And also, if you were to examine, since V equals I times Z, Z has got a negative angle because of the capacitance, we see that theta minus phi is going to be a negative value. Theta minus phi is going to be a negative value. If you were to draw the current phasor and the voltage phasor on the complex plane, you get a diagram that would look something like this, and you see that theta minus phi, of course, is a negative number. And then if you were to watch these currents go by on the oscilloscope, then you would see that the current would peak first, then the voltage would peak as they went by, because they're sinusoids, because of the phase angles. And so we like to say that the current leads the voltage. The current leads the voltage. Again, power factor is the cosine of theta minus phi. We don't want to, cosine's an even function. We don't want to lose that information that theta minus phi is negative. And so when we compute the power factor of a capacitive load, then we will say that, of course, the power factor is going to be a number less than 1. But then we're going to say that that power factor is a leading power factor to represent the fact that it's a capacitive load. And finally, if you were to draw the complex power in the complex plane and look at it, you would see that the reactive power is negative. And so what we like to say something, now reactive power is simply a measure of the power that comes and goes. Remember, there's power that is real power, useful power, does the real work. That's the real part. That's the real power plus J. The reactive power is a measure of the power that comes and goes, that's stored in the field and then returned from the field. Stored in the electromagnetic field for inductors and then returned to you. Stored in the electrostatic field for the capacitors and returned to you. So the reactive power is simply a measure of the power that comes and goes all the time, but we say that an inductive load absorbs reactive power. Now I know it gives it back to you later, but we still say absorbs because of the passive sign convention. It makes it look like it's absorbing reactive power. And we like to say a capacitive load generates reactive power. Again, the Q is a power that comes and goes, but these terms are based on the fact the passive sign convention has an inductive load has positive reactive power, a capacitive load has negative reactive power. Okay, now we're really ready to solve a real problem. So this is something that you may run across at a job. So you have a single phase AC induction motor, and the nameplate on your induction motor, so there's a little plate stamped on the side that's got some numbers on it. It says that this motor is 2 horsepower. It says that it's 110 volts, 60 hertz, and it says that it is a 24 amp motor. And so the question here is, what is the power factor of this motor if the motor has an efficiency of 80%? Okay, the first thing we need to do is figure out what's going on. The horsepower number is, of course, the power output at the shaft. And now a horsepower is a unit. We don't use an electrical engineer. We do everything in terms of watts. We're strictly SI. A horsepower is 746 watts. So a horsepower is right at 3/4 of a kilowatt. So if we have a 2 horsepower motor, then we know the mechanical output of this motor is 1,494 watts. Now this is the power, the mechanical power. This is the mechanical power at the shaft. Now we need the electrical power. Well, the efficiency. Efficiency is normally written as your output power over your input power. Now this is a motor. The output power is going to be mechanical, and the input power is going to be electrical. And we know the efficiency is 80%. We know the mechanical output power is 1,494 watts, and what we're left with is the electrical power. Now, what is electrical power? It's the real power. It's the useful power. So if we have an 80% efficient motor, and 1,494 watts mechanical output, then that means that we can find the electrical power, and that's going to be the real power, the useful power, and that's going to be 1,865 watts. So now we have the average electrical power. So the question is, what's the power factor? Well, we know that power factor is the average power over the apparent power. So in order to find this, we need to figure out what is the apparent power. Well, the apparent power is the power that appears to be in the circuit, assuming you forget all those funny cosine terms and things like that. Apparent power is V RMS, I RMS. And we see, of course, this is an AC motor, so you can assume that all of these values are RMS values because it is an AC motor. So the RMS voltage is 110 volts, the RMS current is 24 amperes, and so the apparent power in this case is going to be 2,640 watts. So now we can find the power factor. The power factor is going to be 1,865 watts divided by 2,640. Oh, I've made a mistake, because this is the apparent power, and the apparent power is not written in watts. Apparent power is in volt amperes. My mistake, I apologize. So the power factor is 1,865 watts divided by 2,640 volt amperes. Of course, watts and volt amperes will cancel. And in doing that, we will find the power factor, in this case, is 0.706. Now, I know this is an induction motor, so it's an inductive load. If we go back to our chart on the previous page, an inductive load is a lagging power factor. So this is 0.706 lagging, to let everyone know that this is an inductive load. So the answer that we're looking for is the power factor is 0.706 lagging. Well, let's do a bonus problem. Let's actually find the complex power triangle for this motor as well. So let's draw the triangle, and you can see when we do this triangle we'll have everything we need. So we draw the triangle. And remember, the apparent power goes up here, and we already figured that out. That's 2,640 VAs. We know the average power goes down here, and we figured that out, and that was 1,865 watts. The angle right there is theta minus phi, and that's going to be the arc cosine of the power factor. So it's the arc cosine of 0.706, and that is roughly 45 degrees. And then over here on the right is the reactive power. And the reactive power we can find two ways. We can say it's the apparent power times the sine of theta minus phi, and we have all the numbers in the triangle. Right there's the apparent power, there is the theta minus phi number. We could do that, or we can just use Pythagoras. It's 2,640 squared minus 1,865 squared, and take the square root of all that. And when you do this, you'll find the reactive power is also about 1,868, 69, and that's going to be volt amperes reactive, and that's simply due to the rounding. It's a 45-degree angle. They're roughly the same, 1868 VAR. And then maybe the question of the day is, what is S? Well, S is quite easy. It is going to be the real part, 1865 plus the reactive, 1868. And the units for complex power are volt amperes, or we can write it in polar form. And in polar form, we have 2,640 angle 45 degrees, and that's also in volt amperes. And so one thing you may say is, well, it's a volt ampere. How do I tell a complex power in volt amperes apart from an apparent power, which is also in volt amperes? And the answer is, it's very simple, because the apparent power is always going to be just a number, And then the complex power is always going to be a complex number or in either rectangular or polar representation. So just by looking at what the value is, it's easy to tell them apart. So remember, your real power is in watts, apparent power is in VAs, reactive power is in VARs, and the complex power is in VAs. Okay, summarizing. Given a magnitude value, we can find what the RMS value is by dividing by the square root of 2. The reactive power, the real useful power is VRMS, RMS, cosine theta minus phi, and the power triangle solves everything. It goes down here. The apparent power is VI. The reactive power is VI sine theta minus phi. Of course, the theta minus phi is the arc cosine of the power factor. Or if you have the S phasor, if you have the voltage phasor and the current phasor for a particular circuit element, you can then compute the complex power, which is VI complex conjugate. And when you do that, it's going to be a complex number. If you view it in rectangular form, it's going to be average power plus J reactive power. Or if you view it in polar form, it is apparent power angle theta minus phi. And so my favorite method for tackling these problems is to compute the complex power and simply write it in its two forms, and then from those two forms populate my power triangle, in which case I can answer any question you want to know about AC power. Complex power VI conjugate is just a wonderful, great shortcut tool to answer all your questions. All right, come back for the next video and we'll do a few more questions about complex power and AC circuits.